We're going to go through a few conceptual questions specifically related to our introduction of Ohm's law and resistors and current. So we have not yet covered resistors in series and parallel, well, as far as specific equations that apply to them, but basic concepts here. So our first question is right here. What do you think the answer is? The correct answer is D. This boils down to what we've talked about with conservation of charge. With current, we're essentially conserving the charge flow. As current is flowing, there's no junctions where some of the current could go one way and the rest could go another way. If there is no junction, then all of the current must keep flowing, and the current needs to be the same everywhere. What ends up being different is a quantity we call the current density. It is how much current per area, per cross-sectional area. So B would have the largest current density. C would have the smallest current density. But ultimately, what's important for us to remember is that the current itself is the same. And that's because there's no junction. There's no other path to split off and take. Our next question right here. What do you think about this one? The correct answer is D. So current is the rate at which charge flows. We can look at the charge per time here. So we're told there's 120 coulombs of charge in a minute, but a minute is 60 seconds. The coulomb per second is an amp. That's why we needed to put the 60 in for minutes, is so that we would end up with amps. So there would be 2 amps of current flowing through this particular wire. I apologize, the size and location is probably changing because I paused to pull in the next question, and for some reason the window is changing the size as well when I do that. So hopefully that's not too terribly annoying. Here's the next question. What do you think the answer is? So the correct answer is D. An ideal battery produces a fixed or constant electric potential difference. How much current flows does depend upon that electric potential difference, but it also depends upon the overall resistance in the circuit. So different circuits with different resistances are going to have different currents. The power ends up being different as well. Here is our next question. Is D. We need 2 amps flowing this way. Now the reason why goes back to conservation of charge, and specifically conservation of charge flow, since we're talking current. This location right here would be considered a junction, meaning as current gets there, technically there's different paths to take. But conservation of charge flow, we have to have whatever's flowing towards the junction continue to flow out of the junction. We call this a junction rule. We can say the summation of the currents flowing into a junction will add up and equal the summation of the currents flowing out. So before we have the answer, the arrows in the picture, I have 5 amps and 2 amps flowing in towards that junction. That's what we mean by in, just flowing towards this location. Our picture shows us 9 amps flowing out. These two sides need to be equal to each other, but they are not yet equal to each other. We only have 7 here. That means we need another 2 amps in to add up to be the 9. And that's why I had to draw my 2 amps flowing into the junction, towards that junction, to make sure that charge flow is conserved. One last question. The answer here is no. So with the way they've drawn this battery, they're showing us that the light bulb is in contact with the positive end of the battery, but there's nothing connecting the light bulb to the negative end of the battery. In order for current to flow in a circuit, there has to be a complete path from the positive end of the battery to the light bulb back to the negative end of the battery. So we would need a connection for current to flow. Since that connection is not there, then no, current cannot flow that way.